Hey there, welcome back to the channel. My name is Chris, and today we're going to talk about color LEDs and driving them from C#. Now, specifically, I'm going to be looking at the WS2812. Adafruit calls it a NeoPixel, but it's the WS2812 controller, which is addressable and lets us set any color to effectively a 3-color LED. Let's go take a look at a couple of these. Here is a pretty common, and this one's actually pretty old, string of these 2812 lights. The 2812 basically has a microcontroller. You can see that square black thing in there. That is the controller for it. And then it has 3 LEDs, a red, green, and blue. And we can address each one of these individually on the strand and set what color you want it to be. Basically, you're setting the intensity of each of the RGBs. So black would be all of them off, white, all of them on. And you've got a 256, 1 byte color. I think it's 1 byte. At any rate, you can set the color for each one. Now, the way to identify these, so before these, there was the 2811, and that was a 4-wire. It actually had 2 different wires for communication. In these, it has a single wire for communication. So we've got a ground, a power, and then the comms. If you're buying these, pay close attention to the power requirements on them. This one, I think, is 5 volt. It probably says somewhere on it. Typically, that's what I buy, but I've seen them 12 volt as well. So make sure that the power requirements for the lights that you are using, you know what they are so that you can feed them individually. Newer ones are showing up in things like this. This has a single 2812 in it, so I can set the color of this band around it. This is a Chromatech switch. You can buy this one. I think I got off of Amazon. I think they are also sold through Adafruit and some other resellers. They all work the same way. You can just drive these as long as you know that it's a 2812. I also have another one over to the side here. It's a reel that's a flat strip that has all of the LEDs on it. You can cut them to length and rewire them together. Same thing with the strand here. You can cut it and rewire it if you need to have a gap in it. You can see here that I have this short piece here wired together with the entire reel. This was for a test before, but it's a good example of how you can wire those together. The important thing is that the outs and ins must match. You can't have the output on one connected to the output on the other side, or it won't work. They are directional. You can see the code here is turning on and off these lights, giving you this animation. So that kind of brings us to an important point of how these work. Let's go take a look at some code. Honestly, driving these is about as simple as you can get. There are some other things that are important to note when you're using these, though, and we'll go over those. But first, let's go take a look at the code for doing this animation that you see in this reel. So here is code running on the Feather V2, and we're going to just use the WS2812 class. The WS2812 is really, really simple. We just create an instance of it, and it uses the SPI bus and then the count of number of LEDs that we have. The count is the number in the string from, the beginning to the end. They will be indexed at LED 0 on, and that'll be important here in just a minute as soon as we look at how we call this. The other piece that we're passing is the SPI bus. Now, using the SPI bus for this is kind of a hack. The way these lamps work is, again, they have a single wire for communication. And if you look at the way the bus works, it effectively has a 0 and a 1 for each piece of data, each bit of data coming. And the way that gets translated onto that 1-wire bus is, I believe it's about 800 nanoseconds high and 400 low is either a 1 or a 0. Then you invert that. 400 high and 800 low is the opposite. I don't remember which is which. We could go take a look at the driver code itself if we really wanted to know, but that's effectively how this works. And then each LED or each, command is 4 bytes of data. Basically, we're telling it which LED we want to address, and then the colors in, I believe, green, red, and blue order. Again, if you're using this driver, the order of the colors doesn't matter. Really, all you need to know is the index of the LED that we're using. So if we use a SPI bus, the reason that we're doing this again is we can't just use a GPIO because there are really, really tight time tolerances, nanosecond level. And managed code just is not going to hit that. If you're going to get a GC or something, it's going to mess with the colors and you're not going to get very good behavior from the LEDs. But the SPI bus is driven by hardware. And so if we take this and then we can calculate what a number looks like to give you those times, 800 and 400, high or low, at 3 megahertz, and then we basically just use the master out controller in line. So the output line from the SPI bus, we're not even going to use the clock, just that single line. And we can fake those numbers by sending one of 2 different numbers to it for on or off. And that will give us the behavior. So really what we're doing is we're hacking a 1-wire protocol using the output or the data out line from the SPI bus. So these are not SPI devices, but we are using the SPI bus to mimic that behavior so that we can control it. Driving them is very, very simple. Basically, we call set LED with the index that we want, 0 being the closest one to the controller. And in this case, we've got 275, so index 274 is going to be the furthest one out from the controller. That's how they're numbered. And then we call set LED to set what we want for the color. That does not turn it on with this driver. What turns them on is a call to show. And when you call show, it will send all of these commands at once as a bulk write. It's important to know that you can't just turn all of them on or all of them off or to some color instantaneously. They will get commanded individually and staggered. So if you have a really long line, you can't turn them all on instantly. You will perceptibly notice that they turn on or off. Basically, they change color, starting near the controller and moving out. So as you're designing whatever you're designing, keep that in mind. Effectively, that's the entire usage of this. Animating is just down to the code of when you turn them on and off. You can see here that this turns them on in different colors, waits 10 seconds, and then just shifts over one and then changes the colors again. It's also important to know that when you set a color, let's say this one here I'm setting to blue at index +1. If I want the previous one turned off, I have to set it to black. These often will come up in an unknown state. They'll come up if there's any noise on that data line. They may come up illuminated at some color. So generally speaking, when you want to initialize, you want to turn them all off or all to some known color and then track the color that you have them if that's important to you. In this case, for this sample, it's really not important. They'll come up in some arbitrary state. Then when the animation runs, it will turn off the LEDs as the animation runs through them. It's very, very simple. As you can see, the code for these is really, really simple, really trivial. It's easy to set up, which is really nice. The thing that you have to be aware of is wiring and power. As I had said, they are directional. And these ones, you can see here, it's got this arrow that is pointing to the direction that communication goes. Basically, this arrow points away from our controller. So if you end up splitting these and cutting a wire, you want to make sure that the arrows on all of them, on both sides of the split, are pointing away from the controller and that you have them wired together. The set I have over to the side here, if you take a look right here at the bottom, it's got an arrow, and that arrow is again pointing away from the controller. it has that arrow all the way along it. You can see it has these copper pads. We can just cut it with some scissors across that copper pad and solder it back together with wires. The other thing that is really, really critical on these is power. Now, these are LEDs, and LEDs are known to be pretty low power, but each one of the 2812, so each colored element actually has 3 LEDs, a red, a green, and a blue. And if they are on at full brightness, each one can consume somewhere around 20 milliamps. That's what you should budget for. So really you could be pulling 60 milliamps for each one if it's on at full brightness. And then if you have a string of 100 of them, let's say, 60 milliamps times 100, you're all of a sudden pulling some serious power. If you're powering that from your microcontroller's power rail directly, you are going to, at best case, brown out your microcontroller and it's going to quit running. Worst case, I've seen it where you actually cook the output on the microcontroller itself. So it just quits functioning. So make sure that you do power budgets on these for how many you're going to have on at a given time, how you're going to drive it. Now you might be thinking, okay, well, what if I have 1,000 of these things together? And in fact, I have done installations where I have over 1,000 of these. If I try to provide 5 volts just at the end, so here at the beginning, you do have voltage drop along the string of lights, and you're going to run into problems. So what I've done is typically every, say, 200 or 300, I will solder in a power supply into that to power the next segment of lights. And again, as long as you have a common ground that comes back, all of them tied together, it'll work just fine. So that is driving a string of them. Let's take a look at how we would hook up something like this button that only uses a single. Now again, because you can hook them up chained together, you can actually hook multiples of these up on a panel and individually control the color on each one through that single data line. Now, if you look at the card that comes with these, how it's wired up, it's a little interesting and maybe not 100% intuitive. I'm going to bring you closer here. You can basically look at the right side of this here as the data side, and then this is the switch side. So common, and then normally open, normally closed. This is for the switch. This is a momentary. They also make them in latching, but this momentary one, the green here, it's on the normally open side of the switch. So right now it is not connected to common, and normally closed, the blue wire is connected. So right now, if I take a meter and I check continuity, there will be continuity between the white and the blue wire. And then when I push it, this will break, and then green to white will connect. And there's probably a state halfway down where none of them are connected. So this is the switch side, and then this is the data side. Fun enough. Pin 1 VDD, the black wire is your positive. It looks like this one can run from 3.7 to 5 volts. 3.7 is kind of nice because a lithium ion battery runs at about 3.7. So it looks like it's designed to run battery operated up to 5 volts. Then we have our data in and data out. Think of this as those arrows on the controller that I showed you before. Data in comes from the controller, and then data out would go to the next LED or the next switch. So if we've got multiples of these in a line, the data in line will be toward the microcontroller, and data out will be away from it, so toward the next lamp, and the last one in the chain, even if it's just one, won't have anything connected to this data out. Then we have our ground. So what I'm going to do is I'm going to wire this up for the data here, and then we'll hook this up to an interrupt digital input. And because we're doing that, this common and this ground will be connected because I'm just going to use a pull up, and then this is going to drive this to ground. I've got the button all wired up here on my desk. The wires are a bit spread out, so it might be a little hard to see, but you can see the data out here, which is orange, and the normally closed, which is blue. Those two are just not connected to anything. Then I have the power coming over to black. I've got the red line here, comes off to this yellow. That comes over and that's hooked to the SPI bus. Let's see, the green is the normally open from the switch. And, oh, yes, the common and the ground are tied together here and they go back to ground. It's sort of green. It's in person, it's very bright green. It's just kind of washed out with the camera here. Take a look at the code for it. It's very, very simple code. So I've got this Chromatech button class that encapsulates basically this hardware. It internally has a WS2812, the index in case you have more than one, and it takes in the SPI bus and this digital port because it derives from push button. So we get both push button behavior and this 2812. And then we can set the color on it. That's really the only difference between it and a standard button. You can see I create the Chromatech button passing in the SPI bus and pin D04. And then on clicked, well, I guess before we do that, we're going to initialize it to this green color. And then when the button is clicked, we're going to change it to the pressed color, which is red, wait 3 seconds, and then revert back to green. Just a real simple animation there. So you can see if I transition back over and we look at the button, it's green. I press it, it goes red. 3 seconds later, it goes back to green. Again, the colors in person are a nice bright green and a nice bright red. So it kind of looks, I guess, orangish here, and I don't know what that is. Maybe it looks bluish white. In person, it's fine. The color difference is just the way the camera's picking it up. So there you have it. Pretty simple to use these WS2812s or NeoPixels from C#. Just have to be careful of a few things like wiring, making sure that you have it powered properly so you don't destroy anything. Otherwise, it's a straightforward application. That's all I've got for you today. Thanks for watching.